This week's topic is all about quantum physics. Well, it isn't really all about quantum physics, in fairness, because quantum is a big chunk of what you'll be studying on a physics degree. This is more just opening the door to it, kind of in the same way that the relativity bit just opened the door to that. So what we really want to do is get across some of the ideas of quantum physics in this one and just look at some of the initial ways that it can be applied. But actually, to get into quantum physics, you need to apply a much higher level of maths, which is, you're looking more at really second year physics degree stuff to properly get into some of the more theoretical aspects of it. So what we're really going to do is look at a few of the basic ideas that underpin it and why it is that you need quantum physics. So the first thing to do is, in the first section, is just get an idea of what we actually mean by quantum. Quantum is pretty much just translatable as small chunk, small bit of. So we're really looking at things that are quite little, but the quantization aspect of it means that things like charge, energy, well, any quantity really, even down to things like time and distance, are not necessarily continuous. They do come in chunks. The easiest one of these to really get your head around to start with is charge. For instance, we can have atoms that have all sorts of charges if they get ionized, but those charges are always multiples of E. They're always multiples of the charge on an electron. And charge is quantized in the value of E, or 1.6 times 10 to the minus 19 coulombs. It comes into energy in this first section with the idea of energy levels. So, just to give you some idea, there's a sort of classical view of an atom, we get beyond the plum pudding and all that, where you've got the protons and the neutrons in the nucleus in the centre, and then you have an electron, like orbiting like a planet around the sun, okay? And planets around stars can basically orbit at any distance they want to. Whereas we know, but probably from doing like GCSE chemistry, maybe, depends what you've studied in the past, that there are orbitals or there are energy levels or shells. It depends exactly how you've studied them. But the electrons are confined and that they can't actually have any position. They can't have any kinetic energy, they can't have any potential energy. They are confined to these energy levels. And all they can really do is occupy one or the other, or they can move between them. And that's where a lot of quantum physics, so certainly atomic quantum physics, comes from, is the knowledge of these energy levels and the movements between them. So there's a whole load of physics that you can go into that goes beyond that. But all this first section does is it introduces the idea of quantization of energy more broadly. And probably the most important aspect, I mean, this equation here is a nice one to start on, but the most important aspect that just goes through all of quantum physics is this second equation. The idea that a photon has an energy that depends on its frequency. Now, that's something you've probably known for a long time. Indeed, it's something that gets taught in Key Stage 3, so sort of years 7, 8 and 9 in high school. The idea that electromagnetic spectrum depends on the frequency. We know that the higher the frequency, the more dangerous things get. So gamma radiation, high frequency, as opposed to radio waves, low frequency. But what you've got to realise is, firstly, all of the things on the electromagnetic spectrum all come in photons. Everything from radio waves, it's just that we don't really see those as photons, all the way up to gamma radiation can be thought of in photons. But what's very important from a conceptual point of view is the next bit. So, section 2 in this chapter, the photoelectric effect. Now, one thing I recommend you have a little look at is search for the PhET animation. It's something done by Colorado University, but they're freely available physics animations, and they range from the absolutely bizarre and inane to some really quite useful stuff, and this is one of the really, really good ones. But this is about the photoelectric effect. Now, it might not make a huge amount of sense to you if you just play with the animation in its own right, but if you get a bit of the context and you understand where it's come from, you can actually see the photoelectric effect at work. So, the main thing I want you to take away from the photoelectric effect is just the idea, once you've understood it, that the only way to explain what we see in the experiment and changing the parameters that we change basically doesn't make any sense if we assume that light is a wave. Now, light is a wave. It has reflection, refraction, diffraction, and interference, all things you've met in the waves chapter. But the interpretation of the photoelectric effect cannot be explained if you change things like frequency and amplitude and observe what we observe. They shouldn't work. The only explanation of the observations that we have from the parameters that we change in the photoelectric effect is light is a particle, and we call that particle a photon. Okay, so that's the really important bit of the photoelectric effect. The experiment in itself, the experiment isn't like an important one about, finding G using a pendulum. It's the fact that it is the way we demonstrate it, the photoelectric effect. It's the way we demonstrate the particle properties of light. Okay, so then it continues a little bit to the next couple of sections to look a little bit more at photons. So if they're treated like a particle, they have an equivalent momentum, which brings us down to this equation here, which you'll have met before, but if you've done A-level physics, you probably wouldn't have met that. You'll have met it in a very different way down here, which will come through in just a second. Okay, so that is all talking about waves and photons of light, which are particle properties of light. Light, which is still a wave, don't forget, but it has particle properties. And that's the fundamental idea of quantum physics. What we've got in the bottom bit of this is the opposite. So this is looking at wave-particle duality, which we generally refer to when we're looking at the wave properties that particles have. And again, there's a few little demonstrations that you need to be aware of that will show it, for example, electron beams being diffracted and things like that. But what the important aspect of this to be most aware of is, again, just this equation down the bottom. So this is the de Broglie wavelength, and this is where if you know the momentum p of a particle, you can get its equivalent wavelength. So where a particle has wave-like properties, it needs to have a wavelength or an equivalent wavelength to decide how it will behave. So this is the equation that gives us the wavelength. So, for example, you can get beams of electrons that will interfere with each other and cancel out like rays of light do. But to do that, or to get diffraction, you'd need a particular wavelength. This is where that wavelength comes from. So there's a relative small amount of information for this week, but it's a little bit more mind-bending to get your head around. Now, the final little bit, the final two sections are, well, the last bit isn't too difficult, actually. It's just putting a few things together. But this little bit is quite an important conceptual idea with just really two equations, more inequalities that underpin the idea of it. This is where you'll start to see what quantum physics is going to look like. We just lack the maths to explain it yet. But this is where you're going to remember this bit when you get into second year of physics undergraduate degree. All these equations are really referring to is uncertainties. So the first one is talking about x is position and p is momentum. And the idea is that we can't really know we can't really know with any certainty the position and momentum of a particle. But the uncertainty in the position and the uncertainty in the momentum is always greater than this value of h over 4 pi. H, by the way, is a constant. H is Planck's constant. And it crops up all the time in quantum physics. The same is true for energy and time. Now, seems like a very different application, but it's still this idea of what we call the uncertainty principle. Essentially, you can bend the laws of conservation of energy a little bit, but the more you want to bend them, the shorter amount of time you can bend them for. So quantum physics is all about, really, these quantizations of things like charge and energy. But they're also about looking at then the probabilities within these discrete possible outcomes. So this doesn't really go horrendously far down any complicated road, but it really does open the door to stuff that you would end up studying in the future. So you've got quite an interesting little set of topics to discuss, but it does take a little bit of getting your head around, and it is worth spending your time on the idea of the photoelectric effect so that you understand what quantum physics is actually all about, and then the rest of it will start to fall into place.